Today I'm going to be talking about how simulation can be used to improve project management. A little bit of my background. For the last 21 years, I've been using and developing simulation tools to help companies improve the performance of their systems. Here's some of the companies that I've worked for and or consulted for, and all of these companies have been heavily invested in the use of simulation to improve performance. I want to give you a little bit of an overview of simulation so that you understand what it does and why we're actually using it. The simulation is a technology to represent how a system will behave over time. And simulation tools provide a mechanism for creating models, and it's a key concept here. We're actually building models that represent real-world systems or some aspect of a real-world system. The simulation models are created by identifying and characterizing the properties and behaviors of the most important components of a system. It's not about representing every detail that can be possibly observed. It's about representing the components that are most central to driving the behavior of the system that you're trying to analyze. The simulation models are used to quantify what the impact of changes to system conditions and policies are going to be on the overall performance of the system. So this talk is about using simulation to facilitate and improve project management. So let's talk a little bit about the concepts of project management that we're going to address in this demonstration today. So we think about projects as being a structured set of tasks intended to achieve a desired set of objectives. And projects are performed to improve the performance of organizations. So there's no reason to do a project unless you're trying to make a change and make a difference. Generally, the difference is you're trying to improve the results, the outputs of your company or organization. And some of the variables we use to track performance at a high level include availability of products and services, also price of products and services. Customers are looking to see that products and services are available when they need them and at the price that they can afford to pay. And they're also expecting a certain level of quality, that those products and services that they get or use are going to perform as expected with the quality that they expect. And then company's got to be able to generate profits, or it's not going to be able to provide products and services to its customers. So we can think about project management as being the process of ensuring that the projects we're performing achieve their performance objectives while satisfying a set of constraints. For example, above, we want available products, we want them at a low price, we want them with high quality, but at the same time, we have to be profitable while achieving these objectives. We're going to spend some time looking at a number of slides where we're going to diagram out performance relations in a business. We have a lot of different aspects of a business that affect performance, and one useful technique for understanding what drives the performance of a business is to look at the relations between the components that are driving the behavior of a business. Performance depends on a network of interacting components. And we use systems relations diagrams to provide a mechanism for identifying the key components in this network and the relations between these components. So in order to work with systems relations diagrams, we need to set the stage and set the table for the type of notation that we're going to use in order to obtain any sense of meaning out of these system relation diagrams. So we talk about components and relations. Here we see two components, and we have an arrow going from component A to B. And what the arrow means is that A has an impact on B because it's pointing in the direction of B. Now we use color coding of that arrow to indicate what type of impact. And here's a situation where we have an impact such that A increases to A will cause increases to B. So we use a black arrow to indicate this positive impact. So we increase values to A, we increase B. If we decrease values in A, we will decrease. So basically we create a similar situation between A and B. We use a red arrow to indicate that we have an opposite effect. So increases to A will cause a decrease to B. Likewise, a decrease to A will cause B to increase. So having set the stage for the notation we're going to use in system relation diagrams, let's look at how we can map out some of these business performance relations. So let's start with market share as kind of a central focus area. What we do as a business is designed to increase our market share. We want more people using our products and services. So we talked before, we're going to introduce some of these higher level concepts. Let's look at how the price that we offer our products and services will impact market share. So as price goes up, we see that we tend to see a reduction in market share. So we have an opposite relation. But as the availability of our products and services increases, we have a tendency to be able to grab more market share. So we have a similar, a like relationship. Increases in availability cause increases in market share. As the quality of our products and services increase, we also tend to increase our market share. So what does market share do to our revenues? Well, we have a positive relationship there. The more market share we have, the more services and products are being purchased, the greater our revenues. What do revenues do to our profits? They increase profits. But now, in order to create available products at the price people want and with the quality that they expect, we have costs. So our costs are negatively related to profits. Increase our costs, our profits are going to go down. And then what is the impact of cost on price? Well, generally, as our costs go up, we tend to have to increase the price of our product, which then is going to give a negative impact on market share. But as the availability of our products increases, in other words, we have more products available to the market and we have more services available. In order to cause this increase in availability, we also have to drive up our costs. Same thing with quality. That if we want to increase the quality of products and services, we're going to have to make an investment. Our costs will go up, and we follow that flow out of costs. If our costs go up, it's going to be likely that our prices will increase, and then we will lose market share. So how does project management fit into this? Well, ultimately, everything we do in a business is directed at having an impact on performance. So let's look at project management and where this fits in. At any given time, most businesses have one or more concurrent projects. Projects might fall into the category of development projects, where we're developing new products and or services. We may have projects that focused on cost reduction. And for example, we may be looking at a manufacturing process where we're trying to reduce our costs while increasing our production output rate and maintaining our quality. Or we may have projects that are focused on problem resolution, basically addressing more of the quality issues of our products and services, where we're chasing after defects and trying to determine ways to reduce those defects. So frequently, these projects must compete for scarce resources, because we have concurrent projects that often have to share resources, and we have resource constraints in a system, so we refer to those as scarce resources. Resource contention causes delays to the start of project tasks, and thus are going to lead to an increase in the duration of a project. So how does the duration of a project fit into performance of a business? So let's go back to our diagram where we were looking at the performance variables, the key performance variables and their relations. And let's drop in project duration. So we're doing projects ultimately to have some impact on availability, price, quality, and profits. Well, we know that if a project's duration increases, we know it's going to cost us more. We're going to have resources utilized for longer periods of time, so our costs are going to increase. Now, if the project is focused on making products and services more available, and we're waiting for the completion of that project, then we know we're going to have a negative relation. The longer the project takes, the less available our products and services will be. Likewise, if we've got a project that's focused on increasing, improving quality, the longer it takes for us to do a project, the less quality we're going to see, the less we're going to have a negative impact on the quality of our products and services. So now let's drill down and look at a little more detail. Let's focus on project duration. What factors affect project duration? Well, we know that a project consists of a number of different tasks. So the duration of individual tasks clearly is going to have a positive impact on project duration. But tasks then have delays. Sometimes we can't start a task because we don't have the resources available that we need to perform the task. So the relation between a task start delay and project duration is also going to be positive. The longer we have to wait for the resources we need to do a task, the longer it's going to take to complete the project. So let's throw in another variable here, resource availability. So how does resource availability affect the task start delays? Well, the more available your resources are, the less likely you're going to have to wait to start a task. So we have a negative relation. Increase availability, decrease your start delays in your tasks. How about another important factor, your resource proficiency, how well your resources are able to perform the tasks in your system. The more proficient a resource is, the less time it's going to take to perform a task. So this ultimately is going to lead to a reduction in project duration because we're going to decrease task durations, it'll decrease the project duration. And there's another factor that comes into play though we need to consider, and that's rework. Tasks are not necessarily done just one time. Often we've got to revisit the tasks because they weren't done correctly. There was a mistake or something malfunctioned, and things have to be done over. So we know that if we increase the amount of rework on a task, that the total duration of that task is going to increase. But resource proficiency tends to have a negative relation to rework. The more proficient a resource is, the greater chance you have at being able to reduce the amount of rework that's going to occur. Interestingly, resource availability, as it increases, the opportunity to have more proficiency amongst your resources is actually going to increase. You reduce the selection of resources that are available, the less likely you're going to have proficient resources performing your activities. So now let's zero down in, let's drill into the details of the factors that actually affect resource availability. So let's look at scheduled resources. Scheduled resources are the resources at any given time that are present, that are able to do work, that have been scheduled to be there to perform tasks. So increase the number of scheduled resources, you're going to increase the availability of those resources. So there's also another important term here, which is resource utilization. A scheduled resource is a resource that is capable of doing work at a particular point in time. A resource that's utilized is a resource that's actually active and performing work. So the greater the utilization of your resources, the less available they are. Resources working on one task can't work on another task, generally can't work on another task at the same time. So the higher the amount of utilization you have, the less available your resources are. So what influences resource utilization? Well, the work required. The more work that's required in a project, the more utilized your resources are going to be, a given set of scheduled resources. And task durations. So if your task durations in a project increase, you're going to have more work required. So that's a primary driver to the amount of work that you have to do. Also, rework. Rework directly affects the amount of utilization of your resources. It's just simply more time that they have to spend redoing tasks that have been done already. Now here's a very important component that we're going to spend a fair bit of time looking at later in this demonstration, and that's allocation policy. And by this I'm really talking about resource allocation policy. Allocation policy as it ultimately relates to resource availability. Now, I've drawn several different relations here, but I put a question mark. We don't know if they're positive or negative relations. It really depends on the design of your allocation policies as to what the impact of an allocation policy is going to be on things such as your task duration, your rework level, and ultimately resource availability. So when we talk about resource allocation, let's look at an example of a resource allocation decision. We have a task 1 that needs to be executed, and at the time that it needs to be executed, we have 3 scheduled resources in the system, but one of them, with the rectangle in red, is resource B that happens to be busy at the time. The ones with the green box are currently idle and are available to do work. So green is an available resource, red is a utilized resource, which is unavailable at this time. So we have a decision to make. We can choose from resource A, B, or C, and there are going to be consequences to choosing all of those resources. If we choose resource A, this is the resource with the lowest proficiency on task 1. It takes 2 hours to do the task, and there's a 25% rework probability. Resource B has the highest proficiency, but it's busy, so we'd have to wait for it to finish doing what it's doing or any other scheduled activities that it has to do before it could start task 1. This is the most proficient because it only takes an hour to do the task and only has a 5% rework probability. Resource C is somewhere in the middle. Takes an hour and a half to do, but a 10% rework probability. So we make a decision. We're looking at all 3 resources, we're looking at their capabilities, and we're making a decision before we actually allocate one of those 3 resources to the task. So ultimately, task duration and rework probability is going to depend on what resource ends up getting allocated to the task. So what's the challenge for resource allocation policies that businesses will design for themselves? Resource allocation policies are absolutely necessary to manage situations where there is contention for scarce resources. The primary objective of designing resource allocation policies and executing them is to accomplish the required work. That you've got a required amount of work that absolutely has to be done for a project, and you want to make sure that your allocation policies are designed in a way that results in the shortest amount of time to do the required work for your projects. So for example, allocating only the most proficient resources to tasks definitely going to reduce your rework and task durations, but it can definitely increase the delays to the start of your tasks. Those proficient resources may not always be available when you need them. On the flip side, allocating the first available resource to a task, always allocating first idle, non-busy, non-utilized resource, is going to reduce the delays to the start of tasks, but can potentially increase your task durations and the amount of rework that'll have to be performed. So in general, what are our project resource management challenges? It's balancing the inherent tension between keeping your scheduled resources utilized while reducing the time required to complete the tasks in a project. So this tension, these things are often in conflict with each other. High resource utilization is not necessarily beneficial. Policies have to be designed to consider the impact of each resource allocation alternative at any given time. And the performance of a project is going to depend very strongly on how these policies impact project duration and costs. So I'm going to present to you a simulation demonstration, and we're going to have a project performance management strategy for this particular simulation demo. We're going to focus on managing project performance by looking at 3 performance variables. We're going to look at the duration of the project, we're going to look at how much it costs to perform the project, and we're going to look at how well we've utilized resources on that project. So our overall objective when we run this project is we want to reduce its duration while reducing costs and increasing resource utilization. We're going to do this by varying 3 things. We're going to vary the number of scheduled resources that we have in the system, the amount of time they work, and the allocation policies. And we can talk about these 3 things that we're going to try and manage as being levers to control the performance of the system. They're input levers. And we see in one lever in one dimension we have scheduled resources, and then for those scheduled resources we have a lever to control the total hours that they work, and we also have a third lever to control how we allocate resources to these scheduled resources. So let's look at some performance variables. We have those 3 performance variables we're looking at: duration, utilization, and cost. Let's look at a 2D plot of project duration versus cost. We're going to get a curve that looks like this, that the less cost we invest in the system, the longer it's going to take to do a project. We have fewer resources available, and it's simply going to take a lot longer to do the project. Going to be a lot of waiting for resources. But if we throw more and more costs at the system to have more and more resources available, we get to a point of limiting returns where the duration of the project simply can't get any less, because there's a fundamental amount of work that has to be done. So I've bracketed out a zone that we want to focus on. We probably want to look at keeping the project duration to somewhere in this range here, which gives us this range of costs. So that's kind of a project management sweet spot that we want to target. Same thing if we look at the other variable, resource utilization, look how it relates to costs. We have a similar curve. We have a sweet spot that we're looking for. So let's overlay these curves. What we end up with is we want to look at kind of the intersection between these two curves and come up with a net sweet spot, and those are the boundaries of costs that we probably want to end up playing with. I don't have any measurements on any of these axes because this is very, very relative. It's a function of what the ultimate goals and objectives are of a business. But you get the idea that we're basically looking for a zone where we're trying to produce the performance that we're looking for with some type of a cost constraint. So for our simulation demo project, this demo project that we're going to look at consists of a network of 9 tasks that have to be performed before the project can be completed. Within this network of 9 tasks, you'll see in the next slides, there will be 3 parallel workflows or paths that make up the project task network. So each task depends on the completion of one or more precedent tasks. Additionally, each task requires resources and time to perform, each task has a specific resource requirement and cannot start until the required resources have been allocated to the task. And the duration of each task is going to depend on the task itself based on the amount of work that has to be done and on the particular resource that gets allocated to perform the task. In our simulation demo, I'll show you how the resources that we have scheduled have different proficiency levels and rework probabilities depending on what tasks they perform. So here's a look at our task network using a Gantt chart representation that I pulled directly out of Microsoft Project. You see the Gantt chart diagram to the right. You see the series of 9 tasks. There are three paths through this network. And you see the properties of the tasks on the left. You see the different durations. You can think about these durations as really being more work levels. This is the amount of work that's required. The actual duration of the task is ultimately going to be a function of what resource ends up getting allocated. And that's where simulation is going to help us quite a bit. It's going to give us an opportunity to play around with a fair bit of variability in the duration of each of these tasks, depending on different allocation policies and strategies we have. Now here we have a simulation model, a screenshot. And this is the simulation we're going to be using. It's XtendSim, and this is a high-level view of the model that's going to be run. This model represents that Gantt chart that we saw at a Microsoft project. And actually, we have a mechanism where we can automate the creation of a Microsoft project Gantt chart to create a simulation model with this structure. Also, I want to point out up in the upper right-hand corner that when we animate this, when we run these simulations, we're going to animate, you will see these green task bars, these horizontal bars, change colors as we run the tasks through the system over time. And these tasks, these green task bars will be in 1, 2, or 3 states. They'll either be waiting for preceding tasks and they'll show up with a blue color. They'll either be waiting for resources, which will show up in yellow, or will be processing tasks. You'll see a red color. A little more detail here on the 9 tasks that we have. I call your attention over to the right where we have a resource requirement, RR underscore task 1, 2, 3, etc. And also a base level default rework that will have a multiplier based on the resource that actually gets assigned. So all of these tasks have the same rework probability, but that's going to change as a function of the resource that ends up getting allocated to the task. Now here's a graph that we should get familiar with because we're going to refer to this several times throughout the demo. And what we're looking at here are the 3 different paths where our tasks are indicated on the y-axis, and time in hours is indicated on the x-axis. And what we're seeing is we're seeing a stacked bar representation here of the sequence of tasks for each one of these paths. And what I'm showing in red is the theoretical duration of that task if you had the most proficient resource allocated to the task. And here you can see that it's path 3 that actually would be the critical path in our system. If we never had to wait for resources and we always consume the same amount of time to perform each task, path 3 would be our critical path through the system, and it would take us 76 hours to complete. Now we're going to look at that same chart. We're going to introduce those other 2 colors, the blue and the yellow. Blue being the total wait for precedence time, yellow being total wait for resources time, and red being total processing time. So let's take a look at path 1 and where we see an indication for slack time here. Right when task 7, if we move from left to right, which is increasing time, we see that task 7 completes, the red bar terminates, and if we go up vertically, we intersect task 8, and we see that task 8 is in a blue color at that time. Well, this is the result of a simulation run, and this is what happened when we ran the simulation. At that time, at 90 plus hours when task 7 completed, task 8 was in a state that it couldn't really start because it was waiting for precedence that you don't see on this particular path. Matter of fact, if you look up, you would see that it was waiting for task 8 is waiting for task 6 to complete before it can start. So task 8, we could derive from these graphs that task 8 has two precedents. It has precedent 7 and precedent 6. So that's slack time. Basically what that slack time is telling us is that it could have taken us a lot longer to do task 7 before we actually changed the project duration as the result of the start of task 8. So that's what we mean by slack time. And we can see that in this diagram, for this particular simulation run, we had slack time in path 3 and in path 1. So for this particular simulation run, path 2 was the critical path. And if we look here, we jump up at the end of each task. We will intersect when we move vertically. We will go into yellow or red color. We won't see blue. There will be no blue. So when we do this simulation demo, we're going to follow an analysis process. First step is we're going to set input values for the 3 levers we talked about: our scheduled resources, how much time they work, and an allocation policy. We're then going to run the simulation. We're going to observe the results for our project performance variables, our project duration, cost, and utilization. And we're going to determine which of the 3 paths is the critical path. And for that critical path, we're going to identify where the longest task start delay is. And what we're going to do is we're going to be focusing in on that yellow color, which is time spent waiting for resources, places where we are forcing a task to delay its beginning because resources that are required are not available. Having identified the longest start delay, we're then going to determine what levers we want to adjust to try and reduce those delays. And then we're going to repeat step 1. So let me give you a little bit of background so you can understand the types of scenarios we're going to be running in order to go through this process that we just identified. Scenario 1, we're just going to look at a baseline. We're going to look at our baseline situation, which has 3 different pools of resources with 1 resource in each pool. So a total of 3 resources. These are our scheduled resources. Remember, that's our 1 lever. We also have time worked. So in our baseline case, all resources work for a 12-hour shift. Then we have an allocation policy for baseline. Each task requires 1 resource from a particular pool. If that resource is not available, the task is simply going to have to wait until it is. So after analyzing how well our baseline scenario performs, we're going to create a second scenario. We're going to end up adding a resource. We're going to add a scheduled resource so that we have 4 scheduled resources. We're going to add a resource to pool 1. Scenario 3 is basically going to be another approach to adding what scenario 2 is, and that is basically adding capacity to the system. You can add capacity by either adding resources or you can add time. So scenario 3, we're going to be actually adding time. We're going to increase the duration of the shift for all the resources. Then scenario 4, we're going to increase shift duration for just the pool 1 resource. We're going to target a particular resource, and you'll see the reason for that in a minute. And then scenario 5, we are going to go back to our baseline and then just play with allocation policy changes. So we're going to go back to having 3 resources all working a 12-hour shift. But then we're going to play games with adjusting our allocation policy to see what kind of an impact that has. So now we're going to switch over and we're going to run the simulation. I'm going to give you a demonstration of that. Here's our simulation environment. Here's our simulation tool, XtendSim. We see an empty space. We don't have a model here. We're actually going to build a model. We're going to auto build a model. We have a little driver program that is going to read a project file. It's going to then read a template simulation model, and we're actually going to build the simulation. When I click the Build Simulation button, you're going to watch to the left. You'll actually see the network of 9 tasks appear as a simulation model. We add the task to the system. We set up some internal data structures, and we've successfully built the model. So the first thing I'm going to do is run. You're going to watch an animation take place here to the left. What we're going to see is we're going to see a project initiated, and you're going to see colors appear in these tasks as the activities move through this network of tasks. So keep an eye on these colors. Red means processing, yellow waiting for resources, blue waiting for precedent tasks. So when we run the simulation, and notice we're actually running several times. This is something we can do in simulation. We're basically trying to accumulate more statistics. You can think about this as basically collecting more data for this particular project, and then we can then look at averages across those multiple runs. The other way you can think about this is maybe a project that is actually going to be repeated over time, and basically we're watching the repetition of that project take place. But here are the results from this particular sim run. So let's stay focused on these outputs. Here are our performance metrics that we're using: duration, cost, and utilization. For this baseline, it's taking us 198 hours to perform the project at a cost of over $75,000. We've got 55% utilization on our resources. Now, if we glance down here, remember what we talked about before with slack time. I can see slack time here. I can see slack time here. I see no slack time in path 1. So we now have a situation where path 1 is the critical path. Now, to refresh your memory, in the baseline, we have 3 different resources that are available to perform 9 different tasks. One of the things I've done in doing this run here is to add some inputs for 2 things that allow us to represent variability in the system. One is the inherent variability of some of the input variables, and in particular, I've got an input for task duration variability. So right now, I have no variability with task duration, and I have something called a random seed value. This changes the sequence of random events in the simulation. It changes nothing else other than the sequence of random events. This, however, when it's non-zero, is actually going to change the length of these red bars. So keep this in mind. Changing this here is going to change the sequence of events, but not anything to do with the actual time that it takes to do a task or any of the other inputs to the system. This is just inherent randomness in a system. And the random seed value gives us a way to go back and rerun the same simulation to produce identical results. But this is just a way of just looking at what inherent variability does to the system. So for example, if I've changed none of the inputs. If we watch to the left, and I'm going to rerun this simulation, I'm going to turn off animation so that we can get a quick result. And we'll rerun the simulation. We see a quick little flicker, and you notice we get exactly the same results. Now, I'm going to change the variability. Let's give up to a 25% variation on our task durations. What this means is every time we're ready to start a task, the simulator is effectively going to roll the dice and produce a duration which is going to vary 25% less or greater than each of these red bars that we see now. So let's rerun the sim. Remember, we're at 198 hours. So we bumped up to 226 hours, and I've not gone into the details of where those changes took place, but this is changing as the result of mostly changes in the durations of these tasks. Here we see we're still with path 1 as the critical path. Go back to 0. Now I want to show you the impact of actually just simply changing the sequence of events in the system. This is what happens effectively what happens in nature. No, things can never be really repeated twice in nature. There's always minor variations that end up producing different results. So let's go ahead and come back to our graph. And let's rerun this and revisit. No variability in task durations. These are going to be our starting baseline durations. All we've done is just change the sequence of events. Wow, we've dropped, look at the duration went from 198 hours to 174. No change in costs. We are changing some utilization here. Just very interesting, right? Just by changing the random seed. So one of the great powers of simulation is we can set up a simulation. Once we've configured the inputs, we can automatically have a simulation run hundreds of times to constantly change the random seed value with each of those hundreds of runs and produce several changing outputs. We can then take the average of those outputs and look at what kind of variability we have so that we have a statistically robust result. Let's do the same thing we did with the other random seed. What happens if we change run duration variability to 25%? Wow, here in this case, instead of increasing the duration, we've actually reduced it to 152 hours. Same cost because we have the same resources in the system, but because we're working less, probably the sum of these red lines has been reduced just because of the variability tended to go short versus long, and we ended up actually dropping utilization by quite a bit. Not as much work that had to be done. So I'm going to set this back up to return to our baseline case. Let's now start playing games by varying some of the inputs. We talked about 3 inputs that we could actually change that represent the configuration of the system. And let's take a look at, I want to take a look at one thing real quickly here, the requirements. And we saw reference to some of these requirements. This is a task requirement, and basically the requirement is how many you need and from where. What are the characteristics of the resource that you need? So task 1 needs 1 from pool 1. Task 2 needs 1 from pool 2, et cetera, and then we kind of repeat the cycle. So we have 9 tasks, 3 different resources to choose from. So here's what we have right now. We have these allocation policies in place. So given that we have those policies in place, if we come here and look at this chart and we say, well, where's our critical path? Well, right now, look, we got a lot of slack time there, quite a bit there. Path 2 is our critical path. So I step back and look at this and I go, boy, there's a lot of yellow here. What does that mean? Well, we're waiting. We're waiting for resources. So I would go to task 4 and go, well, what resource does task 4 want? And we just looked at that a second ago. We see that task 4 wants 1 from pool 1. So let's try something. See, I actually have 4 resources listed here, but I've disabled 1. So I'm only using 3. So let's go and look at what we've got in pool 1. We have one of those disabled resources in pool 1. Let's go ahead and use that resource. So we're going to have to pay more money. We expect the cost to go up. But let's take a look and see. We're at 174 hours duration right now. Let's take a look and see what the impact of adding that. So we dropped 22 hours in the duration of our project. The question that every manager is going to have to ask is it worth the cost to do that? And now we've got quite a few more resources percentage-wise, and that's reflected in a big drop in utilization. We're only 42% utilized. So I would be curious to say, well, what if we try a different strategy? Let's turn that second resource off again. Let's go back to having only 3 resources. And let's actually put these resources on a longer shift. They're currently on a 12-hour shift. I'm going to put them on a 16-hour shift, which coincidentally will be the equivalent amount of cost to actually adding a resource. So this is the same way of getting capacity in the system as adding a resource. It's just adding more time. So we're going to end up having an equivalent cost factor for adding this capacity by way of extending the duration of the shift. So 3 resources, longer workday. Let's go back and take a look at what our impact is going to be. So we're at 152 hours here right now. That was by adding 1 resource. Wow, big drop, big drop. Same cost, because basically we're just increasing the length of the day, which ends up being the same cost as adding a resource with a shorter shift. Tremendous drop in our duration. Utilization sitting there pretty low at 43%. So now I'm pretty pleased with what we've done with duration, but now I'm going to focus in on any way we can get that cost down. Not happy about costs. So what's another strategy we can apply? Well, we know that going back to here, we're still actually seeing a fair bit of wait time around task 4. Actually, we're seeing a lot here. It's not on the critical path because we've got some slack time, but this is of some concern. This is where we're seeing a lot of yellow around task 4. So let's try something else here. Task 4 does not need a resource from pool 2 or 3, and task 7 does not need a resource from pool 2 or 3. So I've now shortened the workday of 2 resources and extended it for only 1. Let's take a look at what the impact of that's going to be. Well, we dropped our duration down to 152 hours from 174. That's good, but not as good as the 126 hours we just saw. However, we're down at $84,000. So this is this trade-off of trying to find where the sweet spot is. Is it really worth paying the extra money to have more resources available, or to keep them busy, or to keep them scheduled longer? So what I'm going to do now is let's go back and say let's go back to the baseline situation and let's see how important this other dimension is, which is allocation policy, which we haven't really explored yet. So let's return this to normal. Let's convince ourselves that we've returned it to normal by running the simulation. And we're back at our 174 hours, $75,000. What I want to do now is simply come in and change the allocation policy for task 4. So we look on this chart here, where is the biggest wait time? We're camped out at task 4, tremendous amount of wait for resources. It's not, once the resource is there, we're not working very long, but we're waiting a good percentage of that time. So let's try a new strategy here. Let's say, you know what, we know that we're waiting on this resource that is not available. And I want to show you something interesting about this. What we're now saying is that we'll take one from pool 1. That's our preference, because we're going to take in preferred order, moving from left to right. So it's going to take from pool 1, but if that resource is busy, we have an or condition here. So we'll take one from pool 2. If that resource is busy, we'll also look into pool 3. What are some of the consequences of this? Well, I'm going to show you something in a table that reflects what the impact of this might be. So we have a table called Resource Task Proficiency. And we've got resources down here. Here's our 1, 2, 3, 4. Remember, only 1, 2, and 3 are in play for this simulation. And here's task 4. These are the proficiency levels of each task. So you can see that task 1 has the highest proficiency level. Well, we drop in proficiency level, which is going to stretch the duration of the task out. This is the way this simulation is running. And curiously, we also have rework probabilities on the task. And we have the same type of table. And we see that the resource 1 has the lowest rework probability on task 4. So we've got an allocation policy now that will possibly engage any one of these 3 resources, but there's going to be a trade-off, right? If we end up selecting a non-preferred, we don't quite know what the impact's going to be at this point in time to our overall project duration. So with that configuration and remembering our baseline results, let's go ahead and run the sim. Wow, not much of a change there. What we saw is that we only reduced by 1 hour just by changing the allocation policy on task 4. Interestingly, look how much we reduced the yellow for task 4, quite a bit. Not for task 7 though. So interestingly, there might be some interference going on here with what's happening because our critical path is now bumped up to path 3. Remember, we were seeing originally one of our baselines, we were at path 1, we switched to path 2 as a critical path, we're now path 3 as a critical path. So one of the things we can look at is we were fixated before on task 7, and we thought, boy, that gave us some gains here for task 4. What happens if we go to task 7 and do a similar thing? Is that going to make any difference? Big difference. And you might have thought maybe not completely expected because we weren't on the critical path and we focused on task 7. The critical path was path 3. Well, guess who's the critical path now? We've now flipped again to now path 2 has become the critical path. So you can see it's almost like whack-a-mole. We throw resources one place, we fix the problem there, and the problem tends to drift. This is a very common occurrence in complex networks of tasks. Here we have a 9-task network. You can imagine how complex it would be if you've got a project with hundreds of tasks and maybe trying to manage concurrent projects all competing for the same scarce resources. So here, notice we've dropped down to 155 hours and we've kept our costs. This is maybe one of the more favorable results we have, and we've bumped our utilization up. So for the lowest cost, we're getting some of the biggest possible gains in the duration of our project. Let's go back to our slideshow. And what did we learn? What have we learned from running this simulation? Some very interesting observations from a very simple model showing some very complex results. A lot of sensitivity in this particular network of tasks. One observation that comes to me is what is the cost to a business of making a system design error by not exploring all the possible design alternatives? We've spent a lot of time poking around here, certainly nowhere near exhausting all the alternatives that could be considered. But you can see for the purpose of this demo, you get a feeling, a flavor for what the process of simulating is. You're basically exploring the design space, looking at alternatives, trying to understand the meaning of how your system is behaving and where to put your energy, where to put your time and resources in order to get the performance that you expect. Additionally, what is the cost of not accurately accounting for variability of your system variables? A lot of the project management tools really don't have any way of handling or representing variability very effectively. Simulation is designed to specifically look at accommodating and representing variability in systems. And we saw how sensitive this system was to two different types of variability. Imagine trying to manage a project in a very complex system where you're just making approximations for variables that have a lot of variability around them. It's going to be very difficult to accurately predict what the duration of a project is going to be. Now, what is the cost of not being able to predict where the critical path will be for a project that is highly sensitive to small changes to the inputs? We saw some very small changes to our inputs. We watched the critical path ping pong around between all three paths, not necessarily in an intuitive way. Maybe with practice and looking at your system, sometimes by looking at that, it becomes obvious, but it's often is not obvious why things would drift and float like that. So if you don't know how your critical path is going to shift and vary in your system, it's kind of hard to be able to have to focus on all your paths through your project network. You'd really like to narrow it down to where your problem areas are and devote and apply your resources to the hot spots rather than to have to cover the entire network. So in conclusion, we've seen that simulation provides an environment to easily perform hundreds of simulation repetitions to provide statistically accurate results for project durations. Simulation also provides a risk-free environment to test the impact of different resource management strategies on performance. So the beauty of this is there are resource management strategies that you could have that you would never try and actually implement in the real world because it would be too risky. These are things that it would be too costly to invest in resources to only find out that it wasn't worth the investment. Whereas in a simulation, you can test a whole range of scenarios and look at what the impacts are going to be with only the cost of developing that simulation model. Finally, simulation provides a mechanism for representing the relations of multiple factors in a system to enable the accurate measurement of the collective impact of these factors on project performance.